Thank you, Lisa. Also, give my thanks to Professor Diane for the invitation. I arrived here the day before yesterday, and this is my third time actually in Toronto area when I working in U.S. This is my first time in Waterloo area, okay, and my first time to this campus. And as just introduced to myself, I was full-time back to China in 2012, joined the USTC. So when I went back to USTC, and I only have one student, and with zero area of lab. So now my lab is bigger than 1,000 square meter, let's put it that way, in areas, and have almost 60 student members in my group. So this is growing. That's why I give the title here is efforts on the oxides, quantum materials, and terahertz development. This is not even right words, because this is too broad. So I just introduce what has been done from 2012, from zero, then expanding to different areas. Okay. So here's what I'm going to introduce to you guys is first the background and challenges, and second is the oxide quantum material, the material system I have been working on for past few years, and also some areas related to terahertz technology side, the developments, and then I give a quick summary. And after all this, if I still have time, I'm going to give a few slides on the Hefei Light Source and the Hefei Advanced Light Source, which was planned to build in the next few years, a really big synchrotron light source, okay? Well, we talk about the chips, right? We have electron-based chips. We call it microelectronics chips. If we talk about the quantum chips, which means inside that chip, we're going to use spin or orbiter or those quantum states for the material has. The problem is, do we have a material base for this quantum chips yet? The answer is, till now, there's no this kind of things. So we need new materials and new functions. That is why we need to put more efforts in the quantum material side. Here I give an example, quantum information storage. If we look at this multi-state information storage, which means we can use the binary system, expanding into 1/8 of different states. So we have called 8 cortex, the memory. This is one of the memory potentially to be used for quantum information memories. Okay, so then we need a material. We just think about this. We need a material which is really good magneto-electric coupling, which means we have a layer in here. We have a layer in here. We're going to cup these spin states. Okay, we need this material. Then this material, for sure, you need to have a single phase. You cannot be like a multi-phase material. And the second is, we need this material have this quantum properties above or at least the room temperature, which will be functioning at room temperature. And this one. And the third one is we need a higher symmetric, crystalline lattice structure. Why we need that? Because you look at this. This is a super lattice. So we have to make materials glue them as a super lattice. So this just give one example. This layer of material, we need this kind of requirements. So do we have this material? Oh, yes or no, okay? This bismuth ferrite is the only pseudo-cubic single-phase room temperature electric coupling material, the only one. But unfortunately, this is shows at room temperature is a weak anti-ferromagnetism. And this is almost conductive. This is a really high leakage. So that means this material is useless for the device fabrication. This is good for physics studying for the research, but not for real. So we need a higher symmetric single-phase ME material. Remember that. We need this material. And with the TC above the room temperature, these three different requirements for future material developments. Then we give the second example. This is a best structure for a spintronics device, okay? We need to have a base layer, then we need to have a ferromagnetism insulation layers, then we have electron can pass through this layer, then we have something called block. This is spin, states. So this is the best structure. Again, we need a ferromagnetic insulator. This is a material, okay? Ferromagnetic insulator material, which means this is the insulator, but this is let the spin, tunneling through. So first, we need this material is intrinsic, is the FM insulation, okay? Then we at least need this material have a transition temperature above liquid nitrogen temperature, okay? This should be better if we can bring it to the room temperature, but it's just hoping to that. Again, if you want to make superlattice in the future, you want to make devices, you need this high symmetric crystalline structures. So we need to grow future into the superlattice. Well, ferromagnetic insulation is naturally is a problem. If we look at this here, this is AFM, this is FM, this is PM, this is DM, okay. Naturally, if this is a ferromagnetic, this is this side, and the insulation is this side, okay. We have to put them on one side. So for lower symmetric ferromagnetic insulators, we do have a few, quite a few. This one, this is a YIG. This actually, the TC is above the room temperature. But this is very difficult to epitaxial grow into superlattices. So this is useless, okay, for the superlattice growth. Then we do need some high symmetric, this material. They have one. This is a European sulfide, European titanate thin films. So this has a really low TC, only 16K. This is from the past research. So this is why I said before, we need to bring this TC at least above the liquid nitrogen temperature, then bring further to the room temperature. This is the way we are pushing through. So this is 2 years ago, there's no, that means now we have something, okay? This, then this is another best structure for a spin wall. This is called exchange bias material. So naturally happen between the anti-ferromagnetic and ferromagnetic interface, okay? This is an exchange bias, which means if we have a hysteresis loop centered at the 0, right? The exchange bias is we're shifting this hysteresis to the left side. Then we have a different bias state, okay? As just the movie showed, let's bring the spins, to other side left. Then we have different resistance, okay? This is a spin wall. Then we also need a material, single phase, just related, what I just mentioned before. We all need this. Okay, do we have this material before? Yes. Look at the past research. In 2006, there's 2 papers. Shows those materials, we just go the temperature here, okay? This one is 5K. This one is, how low is that? Just some 10K or something from here. So we do have this material, but the temperature is really, really low, 2K actually, shows here, 2K. So we, not much this kind of single exchange bias material existed. So the exchange bias effect is still very low, so the temperature is still very low. This is the situation for these three functions, for magneto-electron coupling, for the exchange bias, then for ferromagnetic insulation. These three kind of materials is, are quite a few, for the future quantum material chip if we want to build up something for quantum chips. This is just a few functions. Well, what they're related is this. All those kind of spin-related properties are, we can call them quasiparticles if we have a spin, a wave. They are resonant, all those properties are related to this kind of quasiparticles. So then there's a publication in 2011. We can look at this. All those quasiparticles, all different quasiparticles, the energy lies in 0.1 and 10 terahertz energy area. So that is why if we want to see those quasiparticles that are related to the material property, then we have to work on the frequency range in this range. So that is, and also we need have some other characterization challenges. For example, we have a lattice here, spin charge, orbital, and lattice coupling over here. The space scale is a nanometer, so we need to see very tiny, teeny spots, okay? Then time scale is from picosecond to femtoseconds. Then the energy scale, the resolution you need to have is like MeV. So we need to have this kind of tools to look at that. Not only in terahertz frequency range, but we still need a high spatial resolution, higher time, resolution, and the energy resolution too. So give an example. This is just in Science in 2018. This is not published by my group. This is published by somebody else. So what they did is here, you have this material, erbium ferrites, okay? Then you have a terahertz beam illuminated on the materials. Then we rotate this material. Then we have two modes come out. One is the QFM mode, which means the terahertz, the magnetic field directions align, perpendicular to this spin directions. This is parallel to this, so we have a QFM mode and a QFM mode. Okay, then we find that this oscillation of the spins is right in this terahertz frequency range. This just give you an example, okay? If we want to study what really happens, we need to have this kind of tools. And this just happened in 2018 research paper that come out. So this is the right direction we are look at. So then better terahertz technology are needed. So one is the quantum materials are closely related to this one. Then we need to develop the three different areas. One, we need to have a good terahertz system. Then we need to have a good terahertz source. Then we need to have some good components. This is why my research eventually expanding into all different kind of this, areas. The situation is not that good. For example, if the terahertz source are either too big or too small, /weak, too weak, and it should be compact yet powerful, okay? The terahertz components, we need this actively can control. Then this system, we need, we don't have this kind of system yet with magnetic field can apply on, where a lower temperature can control, then we have a high resolution scanning mode or whatsoever, okay? So the situation, we don't have this kind of yet, so cannot satisfy this requirements yet. So this is the situation. Then in my group, I focus on quantum material and terahertz technology, two sides. This is what we did is, one, we developed a new material system that I will introduce later on. Then we have terahertz FELs. Some of the professors here are interested in terahertz FEL source. Then we have some active components. Then we have the characterization system to be developed in my group. So I move to the second, the material. So the material system I have been working on is a very old material system, which called layered oxide material. How old it is, this is more than 100 years. If this is a bismuth oxide layer, this is a perovskite layers. So we call this a 1 layer, 2 layer, 3 layer, 4 layer, and 5 layer. This system can go as high as 33 layers, make the lattice cell very unstable, okay? So this is you have till last 70s, we have a book from a Russian scientist. There's more than 1,000 materials in this system. So this is one of them, starting from here. Well, I will just go simpler one sense. 99, even more, okay, % of past research studies is on dielectric or the ferroelectricity in this material system. Only a few that are doing this coexistence of ferroelectricity and ferromagnetism, okay? Just only a few. The challenge for the past research is here. The temperature is lower than 150 K. So that is the challenge for the coexistence of Fe and Fm, okay? That coexistence together. So the trans temperature is lower than 150 K. So we need find a good way. First, we make this material system you coexist of Fe and Fm. This is the first one, making them working together, stay together. Then we need make them coupling between each other, make them working together. Then we going to make the working temperature above the room temperature. This is the directions. So we actually in 2009, okay, at that time I still working in US university. So we did realize the coexistence of this Fm and Fe largely over the room temperature. That means both temperature above the room temperature. What we really did is we just use this four-layer system. We adding one cobalt inside, okay? Then we generate a new material. So this material here, you can see this is the Fe polarization, okay? This is room temperature measurements. This is the ferromagnetic. This is room temperature measurement. Both are of the transition temperature is above the room temperature. This is 275 Celsius degrees. This is even higher, 700 something degrees, okay? The problem, we did this, make them stay together, okay? But there's no coupling. This Fe and Fm, there's no coupling observed. So then we made another progress, which is in like 4 years ago. We still use BFCO. Then we find a good Fe host. This is a really good Fe material. So we insert this layer inside here make this 4 layers become 5 layers. We call it SBFCT new material, okay? Let's see how this material does. This is the lattice structure, okay? This is the 4 layers. Okay, we need to look at the dark, okay? The dark, 4 layers. This become 5 layers. This is the old material, it's a new material, okay? So then, this is the FE property, this is hysteresis, okay? You can see there's almost no leakage. And this area is big. This means the charge storage is big, okay? So this is a good FE properties. Then if look at here, this is room temperature. We find the magnetic hysteresis. So now we want to check above the room temperature, how high this can go. We elevate the temperature 100 degrees higher than room temperature, 373. We still have FM and FE, good enough properties. So this is the number. So then we measure at this 370 degrees. We find there do have this ME and MF coupling. Okay, this is a really good material. Till today, this is still the best one from the published records. Okay, so then we made one device. Use this. This is just a ceramics. We made one device. Use this device to use employ this effects. We convert the magnetic signal to the electric signal to realize the detecting of this magnetic field and to read the magnetic record information. So this is the response of this device. So this is a really good material, but this is in ceramics format. This is not for future quantum, chips. So we need to first demonstrate, can we glue this material into a superlattice? The first step is, can we glue into a synchrocrystalline films, okay? So the problem is, as I just explained to you, the unit cell of this material is just like this table, okay? It's really high, but the bottom is small. This is unstable. Then we have a narrow growth windows. That means you have a growth system, the window, that all the parameters for the growth is narrow. Then this bismuth is volatile, okay? So we need to have a way to control this, to reduce this evaporation of this bismuth. Then when the layer number become high, this is not stable. What the not stable means, I'm going to show you later, okay? So then one of my students spent exactly 2 years on this system without any publication, just grew this. Then he changed all the my system, the parameter, the meters, because they're all out of the meter range. We have to use a high, all different meter to detect the parameter, okay? So then we use a substrate. We control the first layer of atoms, okay? If we exactly go through, okay, this layer, then we have a charge field potential go like this way. This is not stable. Then we change it to another layer, okay? Then we have the charge potentials like this way. This is stable. So this is a strategy. You control the first layer of the exposed atoms on the substrate. Here's what we made so far is we grew really good epitaxial single crystalline films, and this is the lattice structures. So we are succeed on make this ceramics into the single crystalline film. So this is not published yet. This is just past a few months we get. On this device, we realized this electron to write and use the magnetic field to read. So this is and make the device working at a room temperature. This is the first one. So not published yet, but anyway, so this is the experiment we demonstrate on this material film. So that is on magneto-electrical coupling side. That material is still not the good one for future chips. The way I look at, because this is still not high symmetric. This is like not cubic, okay? So the growth window is too strict. So that means still have problem in the future. But anyway, we showed something potentially can use for that. So the second progress is we made on the high temperature ferromagnetic insulation. I just give one sentence here. All this ferromagnetic insulation I've been introduced before. But this material, lanthanum cobalt, this is single crystal film in past research. This is high symmetric, cubic, okay? So they have been thinking about this is a good ferromagnetic insulators. And all the papers I said, okay, this Fi effect is related to this defects inside. And then they find transition temperature is really low, just like 10 K or something. So what we did is here, okay, you said this is related to defects. Then how about we grow a thin film? We reduce the defects inside. Well, we cannot claim we reduce full of the defects, but we can reduce the level of the defects inside the film. So we just grew a perfect thin film. So this is a perfect thin film will be made. Okay, this is, you look at almost no defects you can observe from these patterns. Okay, so then you just think about this. On this substrate, we have a structured perfect layer of material. This is just a strand because the lattice mismatch with the substrate. No defects, but it's purely strand films. Okay, then we find this strain-induced ferromagnetic insulation, the temperature is high. From the 10 Ks to 85 Ks. This is the first report. We make this about the liquid nitrogen temperature. In my group, we are keep on this way. So we are still working on grow even perfect, even better. Okay, the films. We try to make this temperature even higher. So this is along this ferromagnetic insulations. Then how about the exchange bias? As I just said, what the exchange bias is like this. You have a hysteresis. Originally, this dark line is here. Then the material shifts to this side. Then you have imbalanced this hysteresis. This material is used for the example I given before for this spin wall devices. Yeah, so this one. Well, for inside this layered structure, we find that if we increase the layer number, okay, from 1, 2, 3, 4 to 10, we are from here. This is 7, 8, 9. We are expecting if we keep increasing the layer numbers, we can shift this exchange bias temperature to the room temperature. The problem is you're getting the number higher. The material is not stable. It's not good. So that is the problem. So what we really did is, okay, this is dynamics. So what we really did, we find another way. We used this instabilities of the structure. We make the material, for example, 4 layer and a 5 layer, the structurally coexistent with each other. They stay together, okay? Then we find very easily, use this strategy, we can move this exchange bias temperature or the room temperature, okay? So this is what we found. So use this, we call the mixed layer, called structural modulations. So this is a good way. This is a good way. So, okay. This is on the material side. I just go really short on this. There's so many publications anyway. So if we make these materials into functioning quantum devices, what the spin-related property would be, and what functions could they deliver? We do not do them yet. So so far we are still measuring the regular properties. So we need to move to the terahertz side. Okay, this is why my group, they move to, on one side we're doing materials, another side we go to the terahertz side. Okay, okay, here's what we have is a terahertz source. How to realize a good terahertz light source? We have many different ways. You have this femtosecond laser, you shoot on a gate, right? You generate the terahertz source, but that is weak, broadband, okay? This is weak. Then we have FELs, really strong, really powerful, but the problem is they are really big. Then we have some tiny, teeny other designs, okay? I'm gonna show you later, some designs, but they are really weak. So we don't have much choice. So one way I followed is here, FEL, okay? So in general, the accelerator-based technology for FELs, there are two ways. One is the oscillator type FEL, the second is the single pass type FEL. This oscillation type FEL normally being effect for the lower photons, for example, terahertz, infrared. For this single pass type FELs normally works for energy higher photons like soft X-ray, hard X-ray. So if you go to Stanford FEL, the 3 kilometers long, they are using the single pass type FEL. But if later, in the next few slides, I'm going to show what been built in my lab is we use this oscillation type FEL. But the bad part is all those two types of FEL is big. The one I just told you is 3 kilometers long. This is a really big one. Okay, even the oscillation type one here, like Felix, this is in Netherlands. Okay, this one is big too. How big it is 30 meters times 20 meters. This is like a room size, even bigger than this room size. So this is hard to use them as a scientific characterization system. So we need to have some way we make them like a table size. Then we can incorporate this into future system development. So this is my invention in past 2 years. So I call this a pre-punched terahertz FEL. What really is, I'm gonna use a femtosecond with synchrotron, the timing between these pulses, okay? So we shoot this on the electric gun, the electrons generated from here being accelerated, then being well modulated in this system here. Then we have a terahertz laser irradiated from the laser here. So if this is a good one, the size can be reduced to like 3 meters plus 1 meter, this size, from 30 meters to 20 meters, okay? So lower cost. That one gonna cost, I don't know how much in dollars anyway, okay? This is could be really cheap. This is lower cost in operation. So the principle of this pre-punched FEL is like this. You have a bunch, like a bunch of electrons that went through this undulator, then they are irradiate. This is in spatially coherent light, okay, terahertz light. So this is pre-punched. So then we have quite a few patents on this. We make this system fully tunable. This laser, you have a small laser here. You need to tune the wavelengths. So first one we change this electron guns, enhancing the harmonic generation. Then second one is we use this mechanism to undulate the size, the gap, okay? So then we can tune the wavelength. So this FEL, we can fully tuning from 0.5 terahertz all the way to like 7 to 8 terahertz, cover the terahertz gap, or cover the terahertz gap. So this is, yeah, they put 5 terahertz here, but anyway. So we also have some other efforts, as I just said. We develop this micro terahertz light sources. This, I just slight skip it, okay? So we have some quite research on that area. But this is just for research, you know, very small, tiny, teeny terahertz, very weak. This cannot be used for the system. Then I have another, you know, a few students that work on this active, you know, terahertz components. Yeah, this is the situation is we have a poor frequency selectivities. We have a low efficiency. We have a low control rates. Okay, this is a lack of efficient manipulation mechanism. So this we need to have some new design. This is might be interest to the lady just left from, yeah, we use plasmonics designing, okay. This is a structure I collaborate with UC Santiago professor, Shaochen Chen. We use this, you know, open and divergent open hole structure to, we call it CDC, okay, this channel, to adjust this terahertz frequency tuning, not tuning, the transmission. We adjust that. Then we make this structures on top of tunable material. For example, we make a dielectric material. You can use microwave to tune it. Then we tune this structure. Then we can tune this peaks through different areas. So this is the structure we made on this strontium titanium oxides. We make this one. So we make this tunable terahertz filters actively, okay, actively, not like this mechanical tuning stuff. Then we have another device developed uses the graphene, okay. One of my students uses Fermi levels and London levels, okay. They're just tuning these levels by the get electric field. So we have a field apply on this. When we tune this, then we have this, the results shows here. We can use a magnetic field to tune it. This is not very efficient. This is high. Use this almost 4.5 T. You know this. But anyway, this shows this can tune. Okay, this can tune, and this also shows we can use this the electric field tuning. We have two ways. One is use the magnetic field. Another way use the electric field to tune this device. Yeah. The filter is good, but the magnetic field is too high. So this is not really realistic anyway. So then we have some terahertz, you know, ultra fast switch based on the plasmonic metal surfaces. This is what they did, the results. So I'm going to quickly skip on this. So this is the results. There's so many, you know, device efforts in my group. They use vanadium oxide. We just tuning this, tuning this terahertz. We use all different kind of designs. Okay. Yeah. Then we have a photo detector based on this quantum material. Actually, we use our oxide material to detect this this one. So this is the component side. Well, I'm more interested in introducing you guys the system. This one's still under the construction spent lots of money, but this is a very interesting one, okay? This one is a standard TDS spectral system, okay? So that is the one I already have in my lab. This is our Terahertz TDS spectral system there. So what we really doing is we're going to build one system. First, we're going to add the magnetic field on, okay? We have a vector magnetic field, like 5 to 9T to this system. Then we're going to put this temperature. We're going to reduce the temperature to how many? 1K or 2K or something, I forgot. Then we have a scanning tip on it to show this really high spatial resolution. So then we add the high throughput, the scanning. So if we have a materials chip like a 1 centimeter size, for example, we have a high spatial resolution scanning all the way to 1 centimeter long distance to check which side are the best, okay? So that is the system we are working on right now. So what we succeed is we first developed this large range high throughput scanning mode. We use a piezo, electric actuators. We can just, just through this thing step by step, so we can all the way go 1 centimeter, okay, the distance. The spatial resolution, we can realize is 150 nanometers. This is in high throughput mode, okay, operating mode. Then on the right side, if we find some area in that sample is interesting, we need a higher spatial resolution. Then we just, step this on here. Then we use FM mode to top down to scanning the area. So this one we already built in my lab. Okay, this tool mode is very successful. Then we have homemade motors for this high throughput. This is just some test this stepler motors, the results, okay, showed here. This is the system I'm talking about, okay? This is a big system. This is like 3 meters high, a big system. Everything is immersed of liquid helium in this tank, big tank. Then Terahertz light goes from inside here, everything inside here, okay? So this is the system we are building right now. So we are expecting this system to be operating next year. So before we go that far, okay, we demonstrate our STM. We called it the compact STM. So this one is a really tiny one. I can just hang this thing, over this door here, then I can still image the atoms on the surface. So students can just open the door, close the door, okay? So this is the one. Well, I cannot just say this is that perfect. When we applied the terahertz beam on these tips inside here, the picture become worse. But it's good enough for our property characterization because we don't have much interest at the atomic levels. We need the high spatial resolution for properties, okay? This is still good enough. So that is the situation here. Okay, so this is on the terahertz development side. Then what I didn't show here is we still build one infrared FEL inside my lab. That one, we just have the light out this week. So there are covers from middle infrared all the way to far infrared FELs. So next time you visit USTC, you can see that FEL. So that is what I have today. So the summary is here. The challenges in quantum material and Terahertz frontiers was briefly introduced. Then we have some results on new layered oxide materials being introduced here. Then we have some low-cost and compact Terahertz FEL efforts. Then have some active components. Then we have some near-field terahertz, scanning system with low temperature and high vector magnetic field. So past how many years? 6 years. This direction, my group, we have 200 publications. And this is my part of my group member. They're beautiful young girls over there, yeah. So this is the group. Well, before I end my presentation, I'm going to introduce a little bit of the Hefei Light Source. We have a Synchrotron light source in Hefei. So that is an open user facility. So this is why I introduce to you guys. This is the first one dedicated synchrotron radiation facility in China. This construction was started in 1984, before you went there, right? So the energy of storage range is 0.8 GeV. So there's from infrared to the soft X-ray. Okay, we cover deep EUV, this wavelength bands. So that's our parameters now, the machine. Okay, this is just second generation synchrotron light source, but this is running at the third generation status. So we have 10 different beam lines. This is infrared, combustion flame, mass spectrometers, soft X-ray microscopy. We have 10 different beam lines. This is all open to the users. And this is what that looks like. So then this is the long wave FGL. This is the one. We just have the light out. We have a FGL built here. This is a gun. This is accelerator, all the way. Then this is the undulator. This is the undulator. We have two arms. One covers the shorter, wavelength band. One covers the longer wavelength bands. Then we have all the conductor light to the other room. There have all different kind of. Then this is the terahertz I just introduced. This is going to light in this area, okay? Then inside the whole radiation shielded buildings, because the radiation is really high. So this is inside the shielded buildings. So this is the effort. Then we have some big planning. We're going to build the future, really good one, okay? Synchrotron light source in Hefei. So this one is the designing. The storage ring here is almost 700 meters long for 2.4 GeV. That will be only one in the world. Is diffraction limited plus 4 band is coherent. Okay, is coherent. So this is a light source here. This land already become real. Yeah, the city gives this 1100 mole. How to convert into echoes? Divide by 60 or something. Yeah, in echoes. Okay, the land already become real. Then the research plan for this one, we just get the full funded from the central government, which is about $50 million US. So for the research plan. So the timelines, this is the present physics designs, the numbers, okay? The timeline for this, we're going to start the construction in 2020, 2 years later. Then end this construction in 2026. So in that time, we're going to have a new light source, okay? So yeah, it's right in time. So I finished my presentation here, and thank you very much.
Thank you so much for that very informative and interesting talk. I'll open the floor for questions.
Just out of curiosity, for your benchtop FEL for a terahertz system that you have, what sort of energies, what sort of powers do you get out of that?
Because this one we can get really powerful, actually. So for the measurement system, we don't need that kind of powers. So in my design, we use the Terahertz power is, this is still continuous wave mode, but this is pulse, okay? We talk about 150 milliwatts. They're very powerful one. Yeah, but we can even go higher, okay? But we don't need that. They're gonna burn the sample. Yeah. Yeah.
More questions? Yes.
Yeah. So thank you very much for this, very fabulous talk, covering lots of interesting subjects. I have a few questions. First one is regarding your materials.
Mm-hmm.
Then you talk about this layered structure. What kind of methods you are using to grow these materials? Are you using chemical vapor deposition, or we are not familiar with the ceramic materials?
Oh.
So we don't know how to grow these materials.
Yeah. We have a post-laser deposition system, but we make them like MBE, okay? We call the laser MBE growth system. That is a very expensive one. Cost me like $2 million for that system. Yeah. Then grew my material, as I just explained. I have to replace all different kind of parameter, monitors, because this is all out of the measurement range. Yeah, it costs a lot.
Yeah, what kind of substrates you are using to grow?
This is just regular sites, because we talk about this one, A and B, right? They are just like cubic, the standard cubic material. If we don't talk about C, okay? C is too long. So we want the structure landing on the subject this way, all the way up. So we use strontium titanate. We use all those kind of, we even grew something on PMMPT. Yeah.
So you do have this lattice mismatching between the substrate?
We do make them lattice matched to the substrate. No, we let them matched to the substrate. Yeah.
But in one of these, results, you push this TC from 10K to 85K, and you said it's because of the strain-induced effect, right?
Yeah, that is we reduce the layer number to 1, become less than cobalt. Yeah, we reduce the layer number to 1, then become just a perovskite, right? So then we reduce the defect level inside the film. You just grew the perfect film. This is perfect, you cannot make a defect totally free, right? Just reduce the density of the defects, okay? Reduce that. Then you make them like a perfect. Then the slight lattice mismatch generate the strain inside, okay? For example, the expanding strains or compressing the strains inside the film. That strain field, generate this ferromagnetic insulations. Yeah.
So, what layer thickness?
Oh, we talk. Well, quite a few. We have upper thickness limit. I don't remember exactly. For example, if you grew thicker than 50 nanometers, for example, I don't remember exactly, then the effect is going to eventually gone because strain, just disappear. Yeah.
But does the TC have a thickness dependence, like below?
Yes. In my paper on peanuts, they show all the data. But if you want to make device, you're going to make them thin enough. Yeah.
Yeah, regarding this.
No, go ahead.
So regarding this FEL, this free electron laser, I know it's a wonderful tool, but it's producing a broader range in the middle infrared and the far infrared. Is that right?
Yeah.
Okay. Then if we do want a single wavelength, what are you going to do? You're using
It is a single wavelength. It is single wavelength. So this is much better than the femtosecond you generate on electrodes, right? It's much better than that one. It is a single wavelength. This is why I have this tuning method developed. You know, in my talk, where we can change the gap of undulators. We can tune it. You know, tuning the wavelengths. Yeah.
So you certainly use this pre-bunch.
Pre-bunched. Yeah.
Pre-bunch.
Mm-hmm.
What that means, I don't know. This pre-bunch.
That is the word they're using by this FER guys. Okay, they just make like you know, they called the electrons like one bunch of electrons. Okay, so we have 10 bunch of electrons all go the one by one. Then you use an undulator to modulate them, right? Then you have a special coherence. You can realize the special coherence for those generated terahertz waves. Yeah. So that's why they are called a pre-bunch.
Going into these modulators, you actually pre-bunch?
Yeah, we have something just like you know, in a series of this bunched electrons getting there. Yeah.
So that's the reason we can make it smaller.
Yeah, that is why we need to synchronize the pumping lasers. Yeah. Mm-hmm.
So by changing the undulator, can you also achieve polarization of the light? Maybe, you know, meaning you know, get to the circular elliptical polarization depending on the orientation.
Theoretically, yes. The problem is, tell you the truth, this thing is not funny, not serious, because that generate really high radiations damages. Yeah. So if we want to make the undulator to select the different polarization, you're going to add much more power on that. So yeah, you can do that, but it depends on how serious you want it. It's better you can just rotate the samples, right? Why you need to rotate this?
I mean, but you still need to make a circularly polarized light source. If you
yeah, that we can do. Yeah, yeah. Yeah, just you don't want shifting these polarizations by these undulators. You can just rotate your sample right in the far end. Yeah, yeah.
So you can achieve it, but you just you know.
Just don't want make to consuming too much power.
So that means, for example, if you want to do the experiment where you switch from left to right for every single sort of measurement, that's not feasible one, right?
For the light source, is not feasible one. Yeah, yeah. But to the samples, you can do that.
Okay.
Yeah.
It's possible to put an optoelastic modulator at the end of the FEL output?
Yeah, but you know how, this is why I talk about the components here. In the terahertz frequency range, even polarizers, you only have this, matter, what the matter strings, right? You only have that. Then you need to have something strong enough to tolerate my radiations. Yeah.
I have one more shot at the FEL. So when you're talking in terahertz, you showed that you had two bands there, one at something like
that is the infrared.
Or was it in the infrared? Okay. Mm-hmm. But it looked like both of those had about the same
this one, right?
width. No, so not your two undulators. When you're talking about your compact terahertz source, you were showing scanning there and two output.
Oh, okay. Yeah.
I couldn't tell by eye, but normally when you talk about the bandwidth of the system, it's in a percent energy, but it looked like both of those bands were about the same width.
Oh, wait, time
Right?
back.
So do you have like a fixed terahertz width that you're looking at? 0.3 terahertz or something like that for the width of excitation?
Time back. Yeah, this one, right?
Yeah, your radiation frequency looks like they have about the same full width half max, despite the fact that.
You mean here?
Yeah, here. The red peak and blue peak here.
This one, right? Or this one?
Yeah,
Oh, here.
Yeah.
Oh, that is that one. If we use this cavity to tune in this the red one, right? You have limited range. Then what we did is we can design this electric guns. We can enhance our harmonic. Then we use our harmonic So use this 2-1, then we can broad our, at least broad this tuning range here. Yeah.
Yeah, I like how you maintain that same narrow frequency at higher.
Yeah. This one, this is only one place can build right now, Tsinghua University in Beijing. Yeah. Yeah. Mm-hmm.
Okay, we have time for one more question. Okay, if not, please join me in thanking Dr. Lu again.
Thank you very much.